Welcome back to the deep dive. Today we're tackling, well, a really fundamental issue in software architecture. It's about how current ways of structuring software just aren't holding up, especially now with automated code generation from things like large language models.
Exactly. LLMs have really thrown a spotlight on the cracks.
Right. So we're diving into a proposal for a new pattern. It's meant to rebuild things from the ground up, really focusing on making software more legible, more robust, things that LLMs, frankly, struggle with in today's code bases.
That's a great way to put it. It's not just about tweaking things, it's addressing a kind of systemic weakness. You look at benchmarks like SW Bench, and the results are, well, they're pretty sobering.
How so?
Well, something like a third of the issues that LLMs supposedly fixed passed all the tests, but they were just fundamentally wrong, logically flawed.
Wow. Okay, pass the test, but still wrong.
Yeah, and maybe even more telling, over 90% of the problems they did solve successfully. Turns out the solutions were already floating around online. They weren't really generating novel fixes in complex situations.
So they're good at finding existing patterns, maybe, but not so much at careful incremental changes.
Precisely. They struggle with real incrementality, making a change here without breaking something over there, and integrity, keeping the whole system consistent. And a big reason for that is that the code bases themselves are often, well, the paper calls them illegible.
Illegible. Let's unpack that. It's not just messy code, is it? It's something deeper structurally.
Absolutely. Illegible means there's a poor connection between what the code says and what it actually does at runtime. If you can't figure out the impacts of changing one small piece without having to trace through, tons of complex dependencies, that's illegibility.
Okay.
So this new pattern tries to fix that. It's built on two main ideas. These completely independent services called concepts, and then these event-based rules called synchronizations that coordinate everything.
All right, let's start with the foundation then. Concepts. What are they exactly?
Think of them as the core nouns of your application. User-facing things. Post, comment, user, password. Each one handles a specific piece of functionality.
And the key thing is their independence, right?
Total independence, that's the goal. It's about maximizing modularity, which, crucially, shrinks the amount of context an LLM needs to worry about when generating code for one.
How's that different from, say, object-oriented programming or microservices? They aim for modularity too.
It's stricter. In OCO, objects call methods on each other. Microservices often have direct API dependencies. Concepts, though, are designed so you can understand one completely on its own. If a comment needs to know who wrote it, it just holds on to a user ID. But it treats that ID as, well, the paper calls it fully polymorphic.
Fully polymorphic. Okay, hang on. Does that just mean it ignores dependencies? How does that actually enforce zero coupling between these concepts?
It forces zero internal coupling. The common concept gets a user ID, but it makes zero assumptions about what a user is, what state it has, or even if that user concept exists elsewhere. The ID is just an opaque token from its point of view.
Ah, I see. So the concept itself doesn't know or care about the implementation of other concepts.
Exactly. That ID is external information. This strict boundary concepts cannot call actions on other concepts. Period creates really high cohesion within a concept and practically zero coupling between them. And that's what makes it more feasible for an LLM. Its entire world becomes just that one concept's definition when it's asked to write code for it.
Okay, that makes sense. And this leads to how they're specified, right? The paper mentions using a formal style, almost like Alloy or Z. Why go that formal?
It serves two key roles. One, it's clear documentation for us humans. Two, it provides a super precise, unambiguous spec for automated tools like LLMs. The spec details the state like mappings from user IDs to passwords and salts and the actions it could perform with clear inputs and outputs, pre and post conditions.
So if you ask an LLM to code up, say, the password set action.
Its whole job is defined right there in that spec. The state variables it can touch, the actions it can invoke within itself. It dramatically cuts down the complexity compared to asking it to write, a whole tangled controller method that touches everything.
And the implementation rule follows from that. Concepts are standalone services. They manage their own state, but they don't expose it through a million specific getter methods.
Right. They expose their state abstractly. The application layer can query the state relations, but the concept itself doesn't need to know why someone wants the data or who's orchestrating the bigger picture. Avoids that classic getter-setter coupling explosion.
Okay, so if the concepts are islands, totally independent, they can't talk to each other, something has to connect them, that's where synchronizations come in.
Exactly. This is the second pillar. Synchronizations are the connective tissue. They're these fine-grained, event-based rules that handle all the data flow and control between the concepts.
So the actual application logic lives here in these rules.
Pretty much, yeah. And it's interesting how they got here. The paper mentions an earlier idea using distributed transactions, but apparently that was really complex to implement, especially for things that happen later, like sending a notification email.
Right, transactions across asynchronous boundaries are always tricky.
So they shifted to this simpler event-based model. A synchronization basically says, okay, when these specific actions finish, and if these conditions on the system state are true, then trigger these other actions. It's a clear causal link.
My first thought, though, is doesn't this just move the complexity? Instead of tangled code and services, do we get a giant, messy rules engine that's impossible to follow?
That's a fair question. But the key is the granularity and the declarative nature of these rules. They're meant to be small and focused.
Oh, small.
Like really small. You might have one sync rule just for creating a default user profile when someone registers, another separate one for generating their initial JWT token, maybe a third for sending the welcome email. Each rule handles one specific cross-concept interaction.
Ah, okay. So you don't have one massive handle registration rule. You have lots of little ones that trigger off the initial registration event.
Exactly. And that granularity is huge for incrementality. If you need to change how moderation works for profiles, you just tweak the specific moderation sync rule. You don't have to touch the main profile concept or the core registration logic.
And because these rules are separate, they enforce consistency, right? The same logic applies no matter how that initial event got triggered.
Precisely. Define it once in a sync rule, and it applies consistently across the board.
Let's dig into the sync language itself a bit. Since we're moving logic out of imperative code, how do these rules handle everyday things like creating new IDs or dealing with errors?
The structure is pretty clear. Sync name, when actions complete, where state checks bindings, then actions to invoke. That where clause is pretty powerful. It's not just for checking state.
What else does it do?
It handles creating new data deterministically. So for user registration, before you call user register in the then part, the where clause can do something like bind as .user. That generates a new unique ID and binds it to the .user variable ready to be used.
Okay, so it handles initialization cleanly. What about errors? Exceptions in normal code can make things hard to trace. How does this handle, say, a registration failure?
This is where the legibility really comes through, I think. Errors aren't exceptions that break the flow. They're just data. If user register fails, its completion record might explicitly contain an output like error.
Erroram.
So the failure itself is an event.
Yes. And that failure event, that record with the error data, becomes the trigger in the when clause for another specific synchronization rule. Maybe you have a registration error handler sync. It triggers on that error output, and its then clause might invoke WebRespond to send a 422 error back to the browser.
Ah, so the error path is just another declared traceable flow in the system using the same mechanism.
Exactly. No hidden exceptions. It's all part of the same explicit graph of actions and reactions. Makes auditing much easier. Okay, that makes sense for tracing. But what about something complex, like building a web response? You know, the real-world API benchmark needs responses that pull data from multiple places, user info, profile data, maybe a JWT token, all matched into one JSON object. If concepts are isolated, how does a synchronization stitch that together?
That's also handled in the where clause. It acts like a declarative query layer over the state of all the concepts involved in that sync.
So the rule can say, okay, when the user logs in successfully, where I can find the bio from the profile concept for this user and the email from the user concept and the token from the JWT concept. Then take all that bound data and use it to invoke WebRespond with the formatted JSON.
Precisely. You define the data dependencies declaratively in the where clause. The synchronization engine figures out how to fetch that state from the independent concepts, binds it to variables, and then you use those variables in the then clause to construct the final output or trigger the next action. It's like defining a view over the necessary parts of the global state, but without the concepts ever needing to know about each other.
Got it. So architecturally, we have the individual concept implementations, these independent services, and then this central synchronization engine, which sounds like a kind of reactive database keeping track of all these actions and rules.
Yeah, you can think of it as the central nervous system. It's watching for action completions and firing the right sync rules. And to make sure this whole thing delivers on that promise of legibility and integrity, there are a couple of crucial architectural choices.
Okay, like what?
First, naming. It sounds simple, but it's vital. The system insists on using uniform resource identifiers, URIs, for everything. concept names, action names, even argument names.
Why URIs?
Unambiguity. It avoids the mess you get in big code bases where the same name means different things in different places or subtle variations cause confusion. URIs provide a single, clear, global name for every element, essential for reliable tooling and, of course, for AI systems trying to understand the code.
Makes sense. Avoids overloading. What's the second thing?
Runtime transparency. This comes down to something called the flow token.
Flow token.
Yeah. When something external happens, like a user hits an API endpoint, which is typically handled by a special bootstrap concept, often called web-nil, the system generates a unique flow token for that entire transaction, that entire causal chain.
Ah, like a request ID, but for the whole process?
Exactly. And this token gets attached to every single action invocation, every action completion record, and every synchronization firing that happens as a result of that initial event.
Yeah.
It propagates through the entire causal chain.
So for debugging.
You just query the system for that flow token, and you get back a complete directed graph showing exactly what happened, step by step, which actions triggered which syncs, which triggered further actions. Total traceability.
Okay, that covers transparency. What about integrity? Atomicity. What if the synchronization engine crashes right in the middle of a flow? How do you ensure things don't get left half done or run twice?
That's handled by durably recording the synchronization edges. Basically, every time a sync rule fires and invokes a new action, the engine records a link connecting the completion record of the new action back to the completion records of the actions that triggered the sync. This link is labeled with the sync rule's name.
So you have a persistent record of the causal links.
Yes. This record provides idempotency and atomicity guarantees. If the engine restarts after a crash, it can look at these recorded edges and the state of action completions to figure out exactly where it left off for every active flow. It can safely reevaluate which syncs need to fire without running actions multiple times or missing steps. Ensures consistency and reliable recovery.
All right, this sounds compelling architecturally, but how does it hold up in practice? Let's talk about the real-world case study implementing that medium clone, Conduit. What did they find when actually building with this?
Well, the paper highlights a few things. One was just how incredibly granular the development process became. Developers could implement one tiny piece of functionality via a single synchronization rule, test it, and commit it, without needing to build out an entire feature or API route all at once. Hyper-incremental.
Made it easier to build piece by piece.
Yeah. But the really interesting part was how well LLMs performed in generating code within this structure.
Ah, right, because the context was so limited.
Exactly. When they asked an LLM to implement the code for a specific concept, the prompt only needed to include the formal specification for that single concept. The LLM didn't need to know about the rest of the application, the other concepts, or the complex synchronization logic. Its task was just make this small, isolated state machine work according to its spec.
Much less chance of it getting confused or breaking something unrelated.
Dramatically less. It really seemed to validate the idea that reducing context is key for leveraging LLMs effectively in complex software.
Okay, let's get into the bug-fixing story they mentioned. That sounds like a real test of the system's promises, especially the provenance aspect. What was the bug?
It was a subtle but classic kind of race condition, or maybe better described as a temporal logic flaw, common in systems with asynchronous parts. In their first pass at the user registration flow, something went wrong if the user entered a bad password, say, one that was too short.
What happened?
The system would actually go ahead and create the user entity first. Then, later in the flow, the password concept would validate the password, realize it was bad, and reject it. So the overall registration flow failed.
But the user record was already created in the database.
Exactly. So if the user, understandably confused, immediately tried to register again with the correct password,
The system would fail again, saying the user already exists. Oh, that's nasty, an intermittent, confusing bug.
right. But this is where the architecture really shone. The developers took the flow token from one of the failed registration attempts. They plugged it into their tooling.
And got the causal graph for that specific failed flow.
Instantly, the graph visually showed the problem. The registration sync rule was triggering the user register action before it had waited for a successful result from the password validation step, which was handled by a different sync or concept action. The ordering was wrong.
So how did they fix it? Did they have to rip apart the registration controller code?
Nope, because there is no monolithic registration controller. They identified the problematic synchronization rule and the actions involved directly from the graph. They essentially fed this small section of the flow graph the faulty rule and its inputs-outputs to an LLM.
Seriously, they gave the faulty logic to the LLM.
Yeah, describe the problem. This should only happen after validation succeeds, and ask for a fix within the synchronization framework. The LLM proposed the correct change to the synchronization logic. The fix involved introducing a new, dedicated sync rule, maybe called validate registration password, whose only job was to handle the password validation. Then, they modified the original registration sync rule to add a condition. It would only fire if the new validate registration password sync had completed successfully for that flow.
Ah, so a small, targeted change to the rules. Add one rule, modify another slightly.
Exactly. Two small additions modifications to the synchronization layer. They didn't have to touch the underlying user or password concept implementations at all. It fixed a subtle, complex flow control bug in a truly modular way, demonstrating that incrementality and integrity the pattern aims for.
That's a powerful story. It really backs up the claim that this structure helps contain changes, whether they're made by humans or increasingly by LLMs. It reduces the risk of those silent breaking changes because the blast radius of any change is naturally limited and the causal flow is so explicit.
Absolutely. What this concepts and synchronizations pattern really does is enforce those good design principles. High cohesion within components, very low coupling between them that we always talk about, but often struggle to maintain in traditional layered architectures, especially as they grow and evolve. It imposes a structure that fights against that natural entropy.
So it provides better guardrails, making it easier to manage complexity, whether you're a human coder or trying to integrate AI assistants.
Right. Better structure, better control.
Which leads to a really interesting thought the paper ends on. This idea of looking toward the future, towards concept catalogs. What's the vision there?
It's pretty ambitious.
Mm-hmm.
Imagine a future where we have libraries of these concepts, user, post, payment, inventory, that have been rigorously tested, maybe even formally verified, guaranteed to implement their specifications correctly.
Okay, so trusted building blocks.
Exactly. If you have these reliable, off-the-shelf concepts, then maybe the main job of application development shifts. Instead of spending most of our time writing the complex implementation code inside the concepts,
We spend most of our time defining the synchronizations, connecting these trusted blocks together to create the specific application logic we need.
that's the vision. Application development becomes less about low-level implementation and more about high-level composition. You're essentially programming in the language of concepts and synchronizations, orchestrating these pre-built, reliable units.
Treating the concepts themselves as a new kind of high-level programming primitive, that definitely shifts the focus from implementation details to the correctness and design of the interactions between components. A fascinating thought to end on.